Okay, welcome. So this is our first video in our bonding unit, and in this video we're going to be talking about how do we draw Lewis structures the real way and not the fake way, which is the Regents way. How do we draw Lewis structures, and what are some exceptions to the octet rule? So drawing Lewis structures, we have a series of rules that we follow, and if you follow these rules all the time, you'll always have a correct Lewis structure. The key is remembering what the rules are. So the first thing that you want to do when you want to draw a Lewis structure to show covalent bonding, number one, sum up the valence electrons that you have in your species. Then you want to use a pair of electrons to form a bond between each pair of atoms. Typically the central atom will be listed first in the compound, so you want to basically start off by connecting everything with a bond. So you're using 2 electrons to form a bond between however many atoms you have. Then you want to fulfill the octet rule for your outermost atom. So give an octet to everything that's on the outside, not the central atom. Except for hydrogen, we're never going to give an octet to hydrogen. It only has 1 energy shell, so we're only going to give it 2 electrons, which means it's only ever going to form 1 bond. And if you ever give me a hydrogen with more than 1 bond, oh my god, I know where you live. Just remember that. Arrange the rest of to fill the octet rule for the outermost atom. So we give an octet to the things on the outside except for hydrogen. Then, then you basically count your electrons. How many electrons have you used? Go back to the number of valence electrons that you counted up in step 1. The number of valence electrons that you have in step 1, that's the number of electrons that have to be in your structure. So if you give bonds and give an octet to your outermost atom, and then you count up how many electrons you have, if you haven't placed the correct number of electrons, then you're going to put any leftover electrons you have on your central atom. So if there's any remaining, you put them on your central atom. This might mean expanding the octet. It might mean having more than 8. That's possible. That's okay. We're going to talk about when it's okay to do that. But if you go through this process and you count up your electrons and you realize that your central atom doesn't have an octet, then you have to consider multiple bonding. So we're going to look at some examples of that. So this process. Draw Lewis structures for PCl3 and HCN. So we're going to start with PCl3. So the first step, we want to sum the valence electrons. Phosphorus has got 5 valence electrons. Chlorine has 3, but there are 3 chlorines in this. So we're going to do 3 times 7. So that's a total of 26 electrons. That means that our structure for PCl3 has to have 26 electrons in it because it's the valence electrons that participate in bonding. So next, PCl3, well, phosphorus is in the middle. I can tell because it's listed first. The only time the atom listed first wouldn't be in the middle is if the first atom listed is hydrogen, in which case it's on the outside. Think of water, right? H2O, hydrogen's listed first, but it's the O that's in the middle. Typically, the rest of the time, the first atom is the one that's in the middle. So put phosphorus in the middle, and second step, form a bond between the phosphorus and all the chlorines. How many electrons have we used to do that? We have used 2, 4, 6, right? 6 electrons, 3 bonds, 6 electrons. We still need 20 electrons. So the next step, fulfill the octet rule for all your outermost atoms. So I'm going to give each chlorine an octet by giving it 3 lone pairs, because now it has 2, 4, 6, 8. I'm going to do that for each one. And now I'm going to count my electrons. So again, lone pair is 2, a bond is 2. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I've placed 24 electrons. I need to place 26. So I'm going to put any leftover electrons on my central atom. And then I just do a quick check that yes, every atom here has a full octet. So boom, that is the correct Lewis structure for PCl3. So now we're going to draw one for HCN. So it's the exact same process. HCN. Hydrogen has 1 valence electron, carbon has 4, nitrogen has 5, so I need 10 electrons in my structure. Now this one, the atoms are literally in the order that they're listed in the formula. So H, then C, then N. So I'm going to take a pair of electrons and connect the atoms together. So that's 4 electrons that I've used. Then I'm going to give an octet to all my outermost atoms, except for hydrogen. I'm not going to give an octet to hydrogen. It's all set with 2, so it has the 1 bond, it's done. But I'll give an octet to the nitrogen. Now I'm going to count my electrons. 2, 4, 6, 8, 10. Okay, I've placed all my electrons, but the problem is that the carbon in the middle only has 4 electrons. It needs 8. So this can't be the correct structure. So, but I also can't put 2 more lone pairs on the carbon because I don't have that many electrons. I've used up all my electrons and my carbon doesn't have an octet. So I can't add any more, but what I can do is take a lone pair off the nitrogen, and instead of having these 2 electrons be a lone pair for the nitrogen, I can make them a bond in between the carbon and the nitrogen like this. This structure still has 10 electrons, 2, 4, 6, 8, 10, but it's getting better towards fixing the octet rule. But again, this still doesn't work because the carbon still doesn't have 8 electrons around it, still doesn't have an octet. Again, I can't add a lone pair on the carbon because I don't have that many electrons. I only have 10 electrons. That's the amount of electrons I have to have. So I'm going to do the same process again. I'm going to take a second lone pair off of the nitrogen and make it a bond between the carbon, and now I've got 2, 4, 6, 8, 10 electrons, but the hydrogen has got 2, the carbon has got 8, and the nitrogen has got 8. So everything's following the octet rule. We want to follow the octet rule as often as we can, meaning like there are times when we're forced to break it because we just don't have enough electrons or we have too many electrons, but if there's a chance that we can follow it, we're going to follow the octet rule. So other examples. Draw Lewis structures for NO+ and the nitrate ions. So first one is NO+. Same process, same exact process. Sum the valence electrons. Nitrogen has got 5, oxygen has got 6, but this +1, we got to do something with that. Well, that means that there's 1 fewer electron. That's how it has the +1 charge, right? It lost an electron. So we're going to subtract an electron from that because of that charge. So we're only going to have 10 electrons in the structure. So we have N and O. We're going to connect them with a bond. We're going to give an octet to the outermost atom. Well, no, there is no outermost atom because there's only 2 atoms. So now I'm going to give an octet to my most electronegative atom because that will preferentially have electrons over the less electronegative atom. So that's oxygen. So I'm going to give an octet to the oxygen because it's more electronegative. I've placed 8 electrons so far, so I'm going to put the other 2 on the nitrogen. But this structure is wrong because the nitrogen doesn't have an octet. It only has 4 electrons, so I have to fix that. So I'm going to take these lone pairs and instead make them bonds between the nitrogen and the oxygen, because now I've got 2, 4, 6, 8, 10 electrons, which is the number that I need, but now everything has an octet. This is an ion, though, so to indicate that's an ion, I'm going to put the Lewis structure in brackets and put the charge on the outside to indicate that that charge belongs to the entire ion rather than just the nitrogen or just the oxygen. So there we go, that's the NO+ ion. Now we're going to do the nitrate. So nitrate, N has got 5 valence electrons. Oxygen has got 3. I'm sorry, there's 3 oxygens. Each one has got 6 valence electrons. But now that -1 charge on the nitrate, that means that there's an additional electron, an extra electron. So now we're going to add 1 to that to have a sum total of 24 valence electrons in our structure. Nitrogen goes in the middle, comes first in the formula, and the oxygens are going to go around the outside. So I'm going to start by connecting the oxygens to the nitrogen. So I've used 6 electrons to do that. Then I'm going to give an octet to all my outermost atoms. So 3 lone pairs on this, just making sure everything has got 8. And then I'm going to count up my electrons. How many electrons have I placed? I've placed 24, right? 8 for each oxygen if you include the 3 lone pairs and the bond. I've placed a total of 24 valence electrons, which is the number that I'm allowed to have. But the nitrogen does not have an octet, so that's problematic. So I'm going to make one of the lone pairs into a double bond between the oxygen and the nitrogen, like that. Now, undoubtedly a question that you're thinking right now is, does it matter which oxygen I take the lone pair off of to make into a double bond? And my answer for this video is no, but we're going to be talking about in the next video what this is called and how you deal with it if you have multiple ways that you can make that double bond. So now we have the nitrogen having an octet and all of the oxygens having an octet. So this is our Lewis structure. It's got 24 valence electrons, and we're good. Exceptions to the octet rule. So in Regents chemistry, you're basically taught that if you broke the octet rule, you'd be tried and hung for chemistry murder, basically. That's really, really not true. So there are many ways that we can break the octet rule. You just have to know when it's allowed. When is it okay to not follow the octet rule? Because like I said, we're going to follow it as often as we can, but we understand that there are times that we just can't. So we have three types of exceptions. First of all, it's entirely possible to have a compound that has an odd number of electrons in it. And if you think about that, there's no way that every atom can get 8 if you have an odd number of valence electrons in your structure. So the way you deal with that is you want to ensure that your most electronegative element in the compound will have a full octet, and your least electronegative element, you have to give it just under the octet. So it's going to be quote unquote stuck with just 7. Don't give it 5 or 3, and don't give it more than 8. Don't give it 9. So find a way to get your least electronegative element as close to 8 as possible without actually going over. So 7. So it's less electronegative, so it won't quote unquote mind as much. Next up, you can have a situation where your molecule, where you have an atom that's going to be stable with less than 8 electrons. And boron is the big one that I want you to know. Boron is actually going to be stable with 6 valence electrons. So boron's okay if it only forms 3 bonds. It's actually more stable, a little more stable that way than it is with 8 because of something called formal charge, which is coming up in the next video. You can also have molecules where an atom will have more than 8 electrons around it. Now this is very important because this is the most common exception that comes up. Only certain elements on the periodic table can do this. Only elements that are in the 3rd period of the periodic table or larger, meaning they're in 3rd, 4th, 5th, 6th, 7th, etc. So basically starting with sodium and anything bigger, but non-metals because we're talking about covalent bonding. Only elements in the 3rd period or larger can exceed the octet. And the reason why it's 3rd period is because as soon as you get to period 3, then you're in n equals 3, which means that you not only have S and P, but you also have D. And S and P together, that's where octet comes from, right? Full S and full P, 2 plus 6 is 8. And it's having that full 8 that tends to make things stable. But if you have a D subshell, even if it's empty, it's still there. And so elements that are in period 3 or below on the periodic table, so period 4, 5, 6, etc., they have empty d orbitals that they're not using. And they can use them for bonding. They can sort of pull out their empty d orbital and say, oh, okay, we need to make more than 4 bonds, so I'm going to grab a d orbital and use that for the bonding. Huge point. 1st and 2nd period elements can't do this. They don't have electrons in the 3rd energy shell, so they don't have these ground level empty d orbitals. So things like nitrogen and carbon and oxygen, they're always going to form 4 bonds. They can never exceed the octet. So that's a really, really big point. So just some examples, drawing some Lewis structures of things that are exceptions to the octet rule. So BH3, boron trihydride, sum of the valence electrons. Boron has got 3, hydrogen has got 1, but there are 3 of them, so that's 6. I mean, right away, we don't even have 8 electrons in our structure, so we'd put the boron in the middle, we put the hydrogens around it, use a pair of electrons to connect everything, sum up the electrons, 2, 4, 6, and that's it. I mean, you're done. You've placed the 6 electrons, and that's it. I mean, you can't add any more. So, boom, that's the structure. And boron's actually stable that way. Next up is ICl5. So iodine has got 7 valence electrons. Chlorine also has 7, but there are 5 of them. So we have a total of 42 electrons that are in the structure. Iodine goes in the middle, and the chlorines will go around it. So use a pair of electrons to connect them. So I've used 2, 4, 6, 8, 10 electrons to do this. Give an octet to all the outermost atoms. count up the electrons. How many electrons have I used to do this? I've used 40 to do this. I need 42, which means I need 2 additional electrons. Where are they going to go? I'm going to put them on the iodine. I'm going to put them on the central atom. Additional electrons will always go in the central atom. It's okay for iodine to have more than an octet because iodine is in period 5, which means that iodine has empty d orbitals, and that's exactly what it's doing right here. It's using its empty d orbitals to make those this additional bonds. Rather than just 4 bonds, it's making 5 bonds and has a lone pair. So that's where that's getting pulled from.